This is John Black, Super Chemist. This is just a disclaimer to let you know that this video is not intended to be imitated. No parts of it should not be copied or done by you or anybody. It's just for educational and maybe entertainment purposes to watch. That's it. I don't condone anyone repeating anything in the video. This lesson here is about making symmetrical ethers, okay? Meaning here's an ether right here. See where I'm pointing? Look at both sides. They're symmetrical. You got an ethyl group here and an ethyl group here, two ethyl groups. That makes it symmetrical because they're the same on both sides. So this isn't just on how to make diethyl ether. This is how to make pretty much all symmetrical ethers. Isobutyl, diisobutyl ether, that's, where you make it from isopropanol. Here there's a lot of side reactions going on. It's not a good reaction. But most symmetrical ethers, especially for small, you can make them like this. So let's go over what we're doing, right? It's just two things, alcohol and sulfuric acid. I want you to notice how I drew these things. These little thingies here are hydrogens, 2 there and 3 there. But I want you to see how I drew this. Look how the oxygen is way over here. The hydrogen's close, and then this one's a middle size. I mean, I didn't look up the bond lengths or anything, but see how much longer this is? This is dangling out here. It wants to do something, but an OH is a bad leaving group, right? But it has these electrons sitting there, right? And as we know, there's no chemical reaction unless there's only one chemical reaction, and that's electron transfer. So this electrons here jump over to this hydrogen here and grab it, right? And these electrons go over to here, right? So now you end up with this. You have a H on here because you grabbed it up from here, right? You have a negative here. This is positive now, right? Because you gave all the electrons to this HSO4, which is negative. So now you have an oxonium ion, okay? And what do we know about oxygen? It's on the right side of the periodic table. That means that it is very, very electronegative, okay? It doesn't want to be positive. Electronegative means it wants to be negative. So what does it do? This less electronegative carbon, it just grabs some of its electronegativity. Now the carbon is positive. And it's surrounded by ethanol molecules. So again, electron transfer. Electrons to lone pair on the oxygen here, just like up here. We're going to jump at this time to this carbon because this oxygen grabbed all the electron density there and pushed it up to here because he's a big guy, he's a big bully, he wants it. Carbon is just, he's kind of wimpy. So anyways, the electrons come in here. Now this is a good leaving group now. It's not an OH anymore, it's a water. And water, that's great, right? So the electrons come up, make this positive into a neutral because you just added electrons, right? It breaks away and becomes a neutral water molecule. These two become connected together, as you can see. You still got an H here. So it's positive, and you still have this, right? It's negative. They counteract. Now, this is an oxonium ion again, right? Since it just has a little hydrogen dangling there, and it has this negative thing here, it just basically gives it back. So now you have your diethyl ether, you have your catalyst, right? Your H2SO4, and then your water molecule. I just brought D to make one. I just brought it down from here. Now this is a catalyst. That means it lasts forever. Of course, that just means theoretically. Okay. In real life, you have all these weird side reactions, and heat is decomposing stuff, and blah blah blah. So it doesn't last forever. Okay. I even looked this up so I can see how you write it. So I always say Le Chatelier's principle. I still don't know how to pronounce it, even though it's right in front of my face. But this Le Chatelier's principle of equilibrium is about this. Because this reaction is an equilibrium reaction. Oh, I guess I should have I didn't put equilibrium arrows, but I should have. Because this is an equilibrium reaction, and that means that once this does this, and it makes so much, I'm going to make up a number here. I'm going to say 50-50%. Let's say it wants 50, it wants 2 of these. For every ethanol molecule, it wants 1 diethyl. And that once it gets to that equilibrium, a 1-to-1 ratio, it stops. Now I'm making up that number. I don't know what the ratio is. So, what would happen if you took some of this out? Let's say you distill some of this ether and this water out, right? Now the ratio, let's say you have 50 here and you have 50 here, right? But now you take out 25 of these. Now you got a 50-to-25 ratio. That's not a 1-to-1 ratio. So it starts making the diethyl ether more and more and more until it builds it up to its 50-50. As you keep distilling it out, now you got it down to 25. Now it starts making some more. That's what they mean by Le Chatelier's principle. But there's 2 ways to shift the equilibrium to the right, to shift it over to this side, to what you want. One is, like I said, remove this stuff here, and it'll keep trying to make it to keep the equilibrium the same. The other way is to add stuff on the left. You can either take out here or add here. I could dump in a whole bunch of extra alcohol, ethanol. And that was my plan up until right now. Maybe about right before I started this video, because it took me a while to write all this crap down, right? And I was thinking, because I asked several times, why are people putting the alcohol, most of it, inside a SEP funnel and dripping it in to, a 50-50 ratio of ethanol and sulfuric acid? And I asked, and I asked, and I asked. I says, the Chatelier would tell you to put more ethanol in to shift the equilibrium to the right. No replies, no answers. It just hit me right now. The reason why you don't do that, because you have to get this up to 145 degrees. Okay, it starts at about 140, say. So you want to keep it between 140 and 145. If you get up to 150, you'll start doing an elimination reaction. You'll start making ethene or ethylene. Depends on what word you like to use for it. But if you keep it, I keep it at 145 the whole time. But the whole point is this: if I need the pot to be at 145 C, and this boils at what, 78 C, how can that be done? It can't be. You know what I mean? If I only put a little bit of sulfuric acid in for my catalyst, because it's just a catalyst, right? So you only need a little bit. And I put mostly ethanol in there, the boiling point is only going to be a little bit above ethanol. So I would distill the ethanol out before I even got this reaction to start going. That's the reason why, I'm guessing, that's the reason why they don't put all the ethanol in at once and then put their little catalyst in. See, if you put 50% ethanol and 50% sulfuric acid, the boiling point will be way above 145. See what I'm saying? You got your boiling point at a 50-50 ratio like that. You got a nice perfect balance where you can get up to 145 and not boil the alcohol away. So anyways, I think that's all there is I could say. I made 1,4-dioxane or 1,4-dioxycyclohexane, whatever you want to call it, either one. It was the same way. It's an ether. And I made it the same exact, showed the same mix. You should watch that video if you're interested in symmetrical ether synthesis. If not, don't worry about it. If you're just into watching this ether, then just watch the ether, diethyl ether. So anyways, let's get on with this. These two tips are really good. The first tip is if you buy round bottle flasks, like I said in another video, the fused silica or fused quartz. Some people call it one, some people call it the other. That's really, making your glass 100 million times better. This is a good suggestion here too. Just for aggravation's sake, you can buy flasks that sit on the table that are flat on the bottom. That way you don't have to ever have, it's such an inconvenience not being able to set your flask down on a table somewhere. You know what I mean? If it's too hot for the table where it might break, you can put a cloth down and still set these down where you don't have to be, it's such a hassle not being able to set these down. I know that, if sphere is the perfect structural, the best thing, and you're losing some structural integrity there, you ain't losing that much. It's not worth the aggravation of not being able to set them down anywhere. But a suggestion, you could use these porcelain or glass bowls like this. The thing about those, though, especially if you have more than one neck, is sometimes if you're walking or something jumps and, vibrates the house or whatever, these sometimes will fall over. Or given enough time, little vibrations will get it to move. So I don't suggest you use those. A good suggestion is tape. See how I got a big roll of tape? You can wait till it gets down, or you can use them just as they are, you know what I mean? But this one's a used one, so I would take it and put it right on there. It's not as apt to slip, you know what I mean? There's more friction with this cardboard than there is between this glass and porcelain or glass and glass. And even with the tape on, it's still, and even if you have a flat bottom, you can still put them on there, you know what I mean? They can fit pretty much all sizes, you know what I mean? Even a 2,000 milliliter, I don't know about 100 milliliter, but they fit a lot of sizes. So let me get 100 milliliter. Okay, they don't fit 100 milliliter. But this is 150 and it fits in there, so, or I think it's 100, yeah, because you got the flat. But that's my suggestion. Get these tape things, thick cardboard, you know what I mean? I wouldn't use like toilet paper or some flimsy, these are thick cardboard. And they work really perfect, man. You don't have to worry about the heat on the cardboard, you know what I mean? You might have to worry about it if you leave the tape on, about heat, but you know what I'm saying? It's a great suggestion. Another suggestion, I wish I had my board here because I've done it, I can't find it. But I just got a flat piece of board, about this big or whatever, and I drilled holes in them, right? But you got to make sure that the hole is not too big so that your round bottom flask hits the table, you know what I mean? You want it so it's high up so there's no, you know what I mean? It's in that hole. But you don't want it too big, too small to where it's going to roll off either. And then you can just set it on, you know what I mean? Just put it right in that hole. See how this isn't touching the table and nothing like that, and be like that. And you have a lot of friction between the wood.